All right, we're going to talk today about rational function. In a previous video, we talked about inverse variations, and an inverse variation is just the simplest form of a rational function. And here are actually three graphs of inverse variations, and you'll see the red one there, and then the blue one, and then the purple one. Okay, and we said that these were not connected pieces, so there's two pieces to each graph. And in these cases, our x and y's could not be equal to 0. Now we're going to take that a step further. A rational function, well, remember, if you remember the word rational, rational means anything that can be written as a fraction. So a rational function is a rule where the quotient it's a quotient of polynomials in which the denominator has a degree of at least 1. So basically what that's saying is there has to be a variable in the denominator. Inverse functions were just a very special type of rational function. This first example right here is an inverse function. These next two are not inverse functions because there's more stuff involved there. So an inverse function is very simple. But these are all examples of rational functions. You will see that the rule is written as a fraction with a variable in the denominator. These next two are not rational functions. Now, this one is rational because it's a fraction, but the variable is in the numerator and not in the denominator. And this one is linear, but in fact, both of these are linear. Okay? All right. With any kind of function, we talk about domain being the x values. We always start out basically saying the domain can be anything, and then except something that's not going to work, something that's not going to make sense. In this case, we're going to call them the excluded values. And that would be any value of x that would make the function undefined. And you should know that undefined means division by 0. So if there is any way that that denominator is going to equal 0, that cannot happen. So in the first one here, the domain would basically be x cannot equal 0, which means that x can be any real number except 0. You can say it that way. In this case, we have to think a little bit harder. We have to look at this denominator and say, okay, what value for x would make this equal to 0? Well, that would be 2. So in this case, x cannot equal 2. Those are our excluded values. Those are the values that would make this situation undefined. Okay, now rational functions are what we call a discontinuous function. That means that they're not connected the whole time. There's some kind of jump or a break or a hole or something like that. And this occurs at the excluded values. So in this case, if y is equal to 1 over x, then the excluded value is going to be 0. If the excluded value is 0, then that means that your vertical asymptote is at x equals 0. And if this cannot be 0, because that would make it undefined, there is no number that we can think of that we can put in here for x that would make y equal 0. So my horizontal asymptote is going to be at y equals 0. Now what an asymptote means is that it is an excluded value, so my graph is going to get closer and closer and closer to that asymptote, but never touch it. Okay, so we never touch the asymptotes. For rational function, the vertical asymptote always occurs at the excluded value. So again, we have to look at the equation. In this case, it's 0. So this is my vertical asymptote. All right? And again, in this case, the horizontal asymptote is y equals 0. Now, we're going to take that and we're going to make a little more sophisticated equation and figure out how to do that. We need to go back and remind ourselves that vertical lines are all written x equals some value. In this case, we're going to let that value be b, and that b is going to relate to a specific number in our function. All right, horizontal lines are all written y equals a constant number, a set number, and we're going to let that represent c. So here is an example right here. Here's an example of a rational function, and we will look at first. Our excluded value is going to be 3. We cannot let x equal 3, so our vertical asymptote is going to be here at x equals 3. Now you'll notice what happened before it was here. That has moved 3 places to the right. So we're going to call this our horizontal shift. We are shifting this 3 places to the right. okay? Then we have this plus 2 on the end, which has taken that from here at 0 and moved it up 2 places. We're going to call that our vertical shift. Now you'll notice that the curve is the same and it heads towards the asymptotes and it never touches, but the whole thing has been shifted over. Okay, so we're going to use that. Now, if we apply that to a general rule, this is the rational function in this particular form. You see your b value is whatever's subtracted from your x, and the c value is whatever's added on the end. And your vertical asymptote will be x equals whatever that b value is, and your horizontal asymptote will be y equals whatever that y value is. So here's an example, okay? All right, so this is supposed to be x minus something. So that's going to make that, we make that minus a negative, and that means that the x value that we're not allowed to use is -7. You can tell that just from here. So my vertical asymptote is x equals -7. All right, there's nothing on the end here, so we just put a 0 there. So my horizontal asymptote is y equals 0. Okay, so let's try this one. This is a little bit more difficult. I end up telling you over here that x cannot equal 3/2. Well, how did I get that? Well, let's take this. Let's take 2x minus 3 and say this cannot equal 0. So add 3 to both sides. That means 2x cannot equal 3. Divide both sides by 2. X cannot equal 3/2. That is my vertical asymptote. All right, and then I have a plus 8 on the end, so my horizontal asymptote is 8. Let's graph this. Okay, here's my vertical asymptote right here at x equals, let's write it down again, x equals 3/2, which is 1 1/2. And then my horizontal asymptote is y is equal to 8. There it is up here. We know that this is a hyperbola. That's what this graph is called, is a hyperbola. So it's going to go towards the asymptote. It's going to look something like this. Oh, that's a little shaky. Okay, this one will be better because I'll just do it like this. And it's kind of like that. Now, that is not good. So what you need to do is you need to pick some values. But you at least, by putting the asymptotes in there, you know what values to pick. Let's pick 3 for x, maybe pick 2 for x, maybe a 4, maybe a 6. You know, pick a couple of values and see what they are. And then come over this way, maybe pick a 1, pick a 0, okay, pick a couple of values and plot those points. All right, but you have the general idea. Now, if this value on the top is negative, so let's make that -1, then what's going to happen is it doesn't change the asymptotes at all. It just simply means that your curves are going to be here and here, okay, if that is negative. Again, from previous lessons, we've learned that the larger this gets, the farther away they get from the center. Okay, and we'll let that be the center right there. Okay, and that would be it.